Welcome students, in this video we will see the design of synchronous mod 6 counter, right. We need to design the synchronous counter mod 6. There are 6 states. Mod 6 mean there is a 6 states are available, right. So we need to identify what is the type of flip flop and how many number of flip flops needed. So the step 1 is determine the number of flip flops needed. So the mod 6 is there, so that n equal to 6. There are 6 states will be there. Number of states will be 6. So from this condition 2 to the power n greater than or equal to n, right. This n is nothing but state, this small n is nothing but number of the flip flops required. So the 6 is there, so we will try with the 3. 2 to the power 3 greater than or equal to n. So 2 to the power 3 greater than or equal to 6, the n is 6. So the 8 is greater than or equal to 6. So this condition is satisfied, right. So we need 3 flip flop. 3 flip flops are needed for this for these 6 states, right. So normally there will be 8 states will be there. The 3 flip flop mean the 0 0 0 up to 1 1 1, there are 3 bits will be available. So here only 6 states are available. So the 7 and 8 last 2 states are taken as a don't care condition, that is taken as don't care condition, right. Now we identify there are 3 flip flops are needed. The second step is type of flip flop. Here we are going to use the JK flip flop. We can use any type of flip flop, but in this problem it is solved with the JK flip flop. The third one is we need to draw the state diagram, right. We need to state the state diagram. So in this given there are 6, mod 6 is there, so thus there are 6 states 0 0 0 0 0 1, that is nothing but 3-bit binary number combination of 8. In that there is 6 is available. This 7 and 8, that is the 6 and 7 is the don't care condition. Here from 0 to 5 available, 6 and 7 is don't care condition, right. So how it is changes, it's a normal binary number, 3-bit binary number 0 0 0 to 0 0 1, then 0 1 0, 0 1 1, 1 0 0, 1 0 1, right. So there are 6 states are available. Again 1 0 1 is changed to 0 0 0, right. So from the state diagram what we are understanding, so this is the current state, this is the next state. We are going to use the flip flop. See this 0 0 0 mean there are, we are going to use the 3 flip flop. You can take this is the flip flop C, B and A, right. For the C flip flop the state changed from 0 to 0, B changed from 0 to 0, C changed from 0 to 1, right. So the B and C there is no change, here also 0, here also 0. For the A flip flop changed from 0 to 1. For this we need to say what is the excitation table, what is the excitation table of the JK flip flop, so that we can decide the input to the JK flip flop. So this excitation table is nothing but we are from the output, that is from current state and next state, we are going to identify what is the input required, what is the input J and K is required, that is the excitation table. Truth table means from input we can identify the output, here from output we are identifying what is the input required. For example, the current state and next state both are 0, there is no change, mean what we need J is 0, K may be 0 or 1, that is X. Suppose the current state is 0, next state is 1, changed from 0 to 1, what we need J equal to 1, K may be 0 or 1, X. Similarly 1 to 0, current state is 1, next state is 0, means what we need J is X and K is 1. If both are 1, current state and next state, what we need J may be X 0 or 1, K is 0, right. So from this we need to identify what is the input to the J and K. For example, see this 0 to 0, there is no change, 0 to 0 mean what we need J is 0, K may be X. For the second flip flop B also 0 to 0, so J is 0, K is X. The third flip flop A changed from 0 to 1, that is this 0 to 1. So what we need, the input to the J is 1, the K is X, right. So this is the next step, excitation table of the counter we need to decide from this excitation table. By referring this state diagram and excitation table, we can frame the excitation table of the counter, right. We say one more, here also 0 to 0 means 0 and X. Here 0 to 1 changed from 0 to 1, 0 to 1 means J is 1, K is X. Then 1 to 0, the current state is 1, next state is 0, 1 to 0, current state is 1, now it is changed to 0, mean what we need the J may be X and K is 1, right. So like that we can identify all, right. So start from 0, it goes up to 6 combination, again it will enter to 0. The 6th, 7th and 8th, that is 6th and 7th position is don't care condition, right. Now we'll go to the excitation table of the counter, right. Now we'll refer both excitation table, state diagram and excitation table of K flip-flop. So this is CBA, current state of the C flip-flop, B flip-flop, A flip-flop. QC plus 1, QB plus 1, QA plus 1. Next state of the C flip-flop, B flip-flop and A flip-flop. This JCKC, that is the input to the C flip-flop. JBKB, input to the B flip-flop. JAKA, input to the A flip-flop. Right. Now this only we are going to identify. Right. So first is 0, 0, 0. Right. That is changed from 0, 0, 1. The current state is 0, 0, it will change to 0, 0, 1, right. Second is 0, 0, 1 is changed to 0, 1, 0, like that we need to write, right. Current state, next state from the diagram, 0, 0, 0 to 0, 0, 1, 0, 0, 1 to 0, 1, 0, right, like that we need to write. So that is very simple. The first column we can write as it is, all 8 combination. The second is nothing but 0, 0 is changed to 0, 0, 1. So this 0, 0, 1 will come here. Then 0, 0, 1 changed to 0, 1, 0. This will come here, right. So the last 2 digit is don't care condition, right. So because it is a 5 counter, 6 counter, 7 and 8 is considered as X, don't care conditions. Now we'll refer this, how to find the input of the 3 flip-flops. Right. I think you are able to understand this is current state and next state. This is a current state, next state. This is a current state, next state, current state, next state. Like that we need to write. That is first column we can write as it is. Second column you have to write like this is the first, because 0, 0 changed to 0, 0, 1. Right. So this is the first combination, second 3, 4, again it will go to 0, 0. Right. Now we'll see this. This is 0, next state also 0. Both are 0 mean what is that? J is 0, K is 1, K is X. See this, J is 0, K is X. Similarly B, that also 0, 0. That means J is 0, K is X. Then third flip-flop A, 0 to 1. 0 to 1 means the J is 1, K is X. So J is 1 and K is X. Right. So this only we are identifying from this excitation table. We can go for one more. 0, 0 mean again it is 0x. 0 to 1. 0 to 1 means 1x, 1x. 1 to 0, 1 to 0 mean x into 1, 1 to 0, here 1 to 0, here x into 1, the input is x into 1. Like that we can identify for all 6 combination, all 6 combination of the this binary number. We can identify what is the input to the C flip-flop, B flip-flop and A flip-flop. This last 2 are don't care condition. Only 6 combination available, 7th and 8th is don't care condition. Right. Now we got the value of JC and KC, the flip-flop C, flip-flop B and A. From this we need to identify what is the expression for JC and KC by using the K-map reduction. Similarly JBKB using the K-map reduction, JAKA from the K-map reduction, right. Now we'll go for the K-map reduction in order to identify the expression for this 6 combination. So for JC, the inputs are QC, QB, QA, the current states. The current states are the input, the output is expression for the C flip-flop J. Similarly, we can go for K, right. So the input is QC, QB, QA. QC having 2 combination, QC bar, QC. QB, QA 2, so that 4 combinations are available. QB bar, QA bar, QB bar, QA, QB, QA, QB, QA bar. That is 0, 0, 0, 1, 1, 1, 1, 0. Right. So from the tabular column it is marked. These 4 are don't care condition. This is 1. So we can combine these 2 cells. If we combine these 2 cells, these 2 row got cancelled. Only we have to refer this. That is KB into KA. So the expression for JC is KB into KA. Similarly, we can go for KC. What is the expression for KC? Right. Here there are 1, 2, 3, 4, 5, 6 don't care condition available. That is, and only 1 is there. This is not only don't care condition. That is the input to the JC may be 0 or 1. So based on that we have cross mark. So we can combine these 4 cell. While combining this 2 column, these 2 rows got cancelled. only we need to refer the second and third column. So QB bar and QB cancel, only QA is available in both, so that KC equal to QA. The input to the KC equal to QA. Now we'll go to JB, the expression for JB, right? So here only this is one, remainings are cross mark. So we can combine these two, right? So while combining these two, what we got? So this you have to refer this QC bar here, QB bar cancel, only QA. So QC bar QA, right? And also we can combine all, so that the JB equal to 1 also, that is also correct. This is another case, only we combine these two, right? QC bar into QA. Then we'll go for KB. For KB, there also this is the only one, others are cross mark. So these four are combined together. Here also we can combine all 8, but here only this 4 is combined. So what we got? QA. These two are cancelled, QB bar cancel, only QA is available. KB equal to QA, right? Now we'll see the JA and KA. So the small correction in the JB, right? The JB not having the all 8 cells are available. So these 3 are zeros, only this is 1, the remaining 4 are cross mark, don't care condition. So that we are combining only these two, there is no other possibilities available, right? These 3 are 0, not X mark. Previously I marked as X, it is not correct. These are all 0. So that we are not able to combine all 8 cells. So that we got QC bar and QA. Similarly KB also, this is 0. So that we are not able to combine all 8 cells. Only we can combine this 4 cell. So that we got KB also, KB is QA, right? So there is a small correction. So here this is 0. Otherwise we can make it as all 8 cell we can combine. So that because of 0 we are not able to combine. Now we'll go to JA and KA. For JA, here all are covered, right? These 3 ones and remaining are cross mark. So that we can combine all 8 cells, so that we got JA equal to 1. Similarly KA also all cells are covered. These 4 are ones. These 4 are cross mark. So that we can cover all 8 cells. We got KA equal to 1. So we got the value of expression for JA, KA, JB, KB, JC and KC. So from that we can design the counter, mod 6 counter, right? So we already discussed there are 3 flip-flops are required, flip-flop A, B, C, right? So this is JA, KA, JB, KB, JC, KC, input to the flip-flop. Outputs are QA, QA bar, QB, QB bar, QC, QC bar. So this is the clock pulse. So the clock pulse is given to all 3 flip-flops, right? Now we need to see what is the input. For JA and KA, the input is 1. 1 is given to JA and KA. What is the input to the JB? It is QA into QC, right? QA, it is available here. QA is directly connected. QC bar, where it is available here, available here. So QC bar is connected to this AND gate. This is AND gate. One input is QA, another input is QC bar. So the AND gate will multiply this, so that QA into QC bar is given to the JB, right? What is that KB? What is the expression for KB? Only QA, right? This QA is given to KB, right? What is the expression for JC? JC is QB into QA. These are all what we discussed from the K map. These expressions are available in the K map. QB into QA. The QB is available here. We have one AND gate. QB is available. Where is QA? QA is available here. This is QA, right? QA is connected. So QB, QA multiplied QB into QA, that is given to JC, right? What is KC? KC input is QA, right? This QA is available here. That is given to KC also, and as well as this AND gate, right? Now the input is given to all 3 flip-flops, so that we can get the mod 6, the counter, synchronous mod 6 counter. The design was completed. So in this video we discuss about the design of synchronous mod 6 counter. Thank you for listening.